Okay, here we are. The first two calculations we have to come up with relative to solutions are two of the more important ones, especially when it comes to acid-base chemistry. You use molarity, okay, relative to colligative properties, which I'll explain in a little bit. You need molality, say that. 1, 2, 3, molality. Say it, everybody. 1, 2, 3, molality. Molarity and molality. Molarity is moles over liter, correct? And molality is moles over kilograms, correct? Moles of what over kilograms of what? Well, the moles of solute over the liters or kilograms of solvent, correct? Understand this, that moles is mass over the atomic weight. People say mass over mole, gram, or gram moles, whatever. It's the atomic weight of the stuff. So, make it easy. Don't go crazy. Try to simplify where you can in chemistry. Okay? Don't go crazy with this stuff. Okay? So let's do a problem. I think I said problem 60B from chapter 16. Genevieve, would you like to read that to me just very quickly?
All right, calculate the moles and grams of the solute and...
Calculate the moles and grams? Is that what you said? Okay. Well, I want to calculate the moles and grams of the solution, which is what?
Of the solute.
Of the solute, right? Solute. Go ahead.
In the solution, 50 times 10 to the second milliliters.
So I have 50, 500, right? 500 milliliters of what?
2.0 m KNO3.
Okay, good. Excellent. All right. I'm going to solve the problem in red. All right. This is what I want to do. I want to find out how many moles and how many grams of solutes are in 500 milliliters of a 2 molar solution of KNO3. Right away, God, the first thing I would do is going to be to write what? Just because I'm crazy. I'm crazy, I know. Don't go there. What's the first thing you would do? Find out what the atomic weight is of potassium nitrate. Right? Potassium nitrate, KNO3, right? Knowing that that's potassium nitrate, I just reviewed chapter 9. Wow, we're doing a lot of review for the final, right? Excellent. Okay, so, what's potassium?
Isn't it K?
Yes, thank you. The K is there, but I'm meaning what's what's the mass number? I thought you guys might be on the same frequency, but you're obviously not on the same frequency. What is the mass number of potassium? Anybody?
39.
30, just mass number. So 39, right? And then nitrogen is what? 14. I have one nitrogen, one potassium. How about oxygen? 16 times 3 is what? 48. Excellent. 48. So 9 plus 4 is 13, plus 8 is, you with me? 9 plus 4 is 13. 13 plus 8 is 21. So that's going to be 5, 6. Is that correct? So that's the atomic weight of potassium nitrate. We'll put that in our back pocket. Okay? All right. Now, this is what we're going to do. That's the equation we're going to use for molarity. Molarity equals moles over liters, correct? What is it we want to calculate? What is it we want to calculate? The first thing we want to do is we want to do moles. Let's do both problems as if, there's two problems here. Let's do both problems as if they're completely independent of one another. What I mean is, I'm going to calculate the moles, which is easy. But I'm not going to use that value to calculate the mass. I could, because I know moles equals this. But I'm going to do both problems as if we're independent of each other. Correct? You get that? So if you're going to do moles, how do you plug into this? You see that this is going to be the extended equation up here. What does that mean? In other words, it's going to be the mass of the solute divided by the atomic weight of the solute. I know chemistry teachers all over the world may be looking at this video and I say that moles is the mass over the atomic weight. They're cringing. Ugh, they're cringing. Ah! Okay, can you hear them cringe? Okay, excellent. And then I'm going to put that over the millimeters of solvent divided by 1,000 milliliters. Okay? Can I do that? Is that okay? All right? So, I'm going to work down here. Can you see that on the, can you see this?
No.
You can't see that? You can? Okay.
You don't have this one.
You can just see it. Okay. How about this? Can you see this? Can you see that? No? All right, well, I'll fix that. I'll just move it. There you go. Excellent. So, the moles is going to, the molarity is going to be the mass. Okay? Actually, what are we doing? We're doing moles first, right? I lost my mind. But what I told you is still okay. That's the full equation, correct? But we can use the simpler one. In other words, we're going to say molarity equals moles over what? Milliliters over 1,000. Which equals what? Which equals what? What's the molarity of the solution? 2. Moles, milliliters, grams, right? Make sure that you have your unit labels okay, and then you can just drop them and do your calculation, okay? So 2 molar, okay, equals, what's going to be 500 divided by 1,000?
0.5.
0.5 over moles. So what is moles going to equal?
1.
1? Are you sure? Cross multiply. So, moles equals 1. Okay? Moles equals 1 mole. Yes? Correct? Correct? Are you okay with that? Now, we could obviously use that to calculate the problem, but what I want to do is, I want to show you the expanded equation and how to use it. Okay, can I erase some stuff here? Is that okay? I can erase pretty much all of this. Okay? I'm going to erase everything. Okay. All right? Are you ready? So, I know that equals mass over atomic weight equals milliliters over 1,000. Okay? So that's going to be, we want to know the mass over, what's the atomic weight? Potassium nitrate?
101.
101. And what are the unit labels for that?
Kilograms.
Just U. Atomic mass units or just a U is fine. Okay? And that's over, what's 500 divided by 1,000? 0.5. Okay, can I erase all this? Okay, and that's going to equal, what's the molarity of the solution? What's the molarity of the solution? What's the molarity of the solution? It's in the original problem. 2 what? 2 molar, correct? So what is 0.5 times 2? 1. So it's mass over 101 equals 1. What's the mass going to be? What's the mass going to be? 101 times 1 is?
101.
Mass equals 101 grams. The way I teach this stuff is you have to have a lot of faith in unit labels. You know, what are the unit labels for these things? And everything works out fine. What are the unit labels for moles? Really? What's the unit labels for moles? The way I do it. A mole equals mass over atomic weight. So the mole would equal grams over, it's not a mu, it's a u. Grams over atomic mass units, right? U, atomic mass units, yeah? Okay. All right, so that's molarity. That's molarity. Let's do another problem, shall we? Okay? All right, let's do another problem. One more, and then we'll do some more. Okay. It says, how about all right, let's say this. Let's do another problem, okay? Let's do another type of problem altogether, all right? All right. All right. There's something called colligative properties. And colligative properties, one of the colligative properties is the fact that in a solution, you can change the physical nature of that solution relative to the nature of the solvent that you began with. Correct? What's the boiling point of water? What's the boiling point of water?
0 degrees Celsius.
The boiling point of water. They gave me the freezing point of water. They're very tired. It's the last day of the work week. 100 degrees Celsius. I hope you know that. Okay? I want you to go jump in a frozen lake that's boiling. Does that make any sense to you whatsoever? Thank God it makes no sense when you hear it out loud. What is it?
Triple points.
Triple. If you could only breathe at that temperature. Okay, so you have the boiling point is 100 degrees Celsius. Okay, and what is going on in water? What is going on in water? It's moving so fast and it's so hot. What's decreasing rapidly? Hydrogen bonding, right? Because you're adding heat, and that's going to decrease the hydrogen bonding, isn't it? Correct? Okay, good. Now, if I add salt to that water, what are you going to increase relative to electrostatic forces? You're going to increase the boiling point, but why? Aren't you increasing, here's water, And the water is going to boil, right? The water's boiling, and it's leaving, isn't it? It's leaving the beaker when it boils, right? But if I put ions in there, like salts, okay, that's chlorine, and I'll put sodium as well. What am I increasing by putting ions in there relative to intermolecular forces? I'm increasing the ionic attraction, aren't I? Aren't I increasing the polarity of the solution, aren't I? By putting things in there? And what effect does that have on the ability of water to escape the fluid? It what? It decreases the ability of water to leave the solution. True or false? It's not hard, right? What do you have to understand? Opposites attract. That's the extent of this, right? So what do I have to add to it to get those water molecules out of there? How do I compensate for the additional salts? What do I use? One word. I can use the H word, or I can use the T word. Both are indicative of the same. Heat. I add heat. Or the E word, energy, or the T word, temperature. You get it, right? Clear? Okay. We may be slightly misusing some of those terms, but this isn't a thermodynamics yet. So we can speak in layman's terms, okay? So the boiling point is going to increase, correct? Yes or no? How much does that boiling point increase? How much does it increase? Is there a constant? Is there a constant which helps you determine how much it's going to increase? Is there? Is there anything that you can find in the chapter that might help you understand what it is we're talking about? Look at table 16.2 on page 542. The boiling point elevation constant. The boiling point elevation constant. It's called K sub B. And what is K sub B for water? You have different solvents in there. You have acetic acid. You have camphor. What solvent is most affected by the addition of a solute? From that table, what solvent is most affected by the addition of solutes? Water? Water is 0.512. 0.512. Genevieve. Camphor. Camphor. You know that stuff you put on your lips for a cold sore? It smells terrible. I don't know if they still use it. It's camphor. Dries you out. Right? Horrible stuff. Brr. Okay? But water is actually very low. 0.512. Okay, what are the unit labels for that? This is what's interesting. Degrees Celsius per molal. So what do we have to know? What do we have to do? If we want to find the boiling point elevation, in other words, I'll leave that on the board. In other words, this is what we want to do. We want to find out, am I still filming? We want to find out, tell me when it goes off. extra credit to Mark if you tell me when it goes off. Clear? Yes? Your assistant is going to be Massa. Okay, now. So, are you ready? What do we have to know in order for us to determine the amount the boiling point is elevated? What do we have to know? We have to know what? We have to know the number of moles of solute, and we have to know the what? The number of, not moles of solvent.
Kilograms of solvent?
Excellent, Genevieve. The kilograms of solvent. Okay? We have to know the moles of solute and the kilograms of solvent. So, what's significant about the moles of solute? What would we have to know in order to get the moles of solute? We would have to be directly given the moles of solute, or we would be given what? The atomic weight and the mass, correct? And we could calculate the moles, correct? Okay. Let's do a quick problem, shall we? Okay, are you ready? All right. Excuse me while is my top of my head blinding you? Okay. You have my permission to wear sunglasses while I'm reading in the book. Okay. It says, I got one. What is the boiling point of each solution? You ready? Write this down. 0.5 moles glucose. 0.5 moles glucose in 1,000 grams of water. 0.5. So 0.5. What did I say? 0.5 moles glucose. And 1,000 grams of what? Water. So what's the molality? First of all, what's the molality? What am I looking for anyway? What is the boiling point of each solution? Okay, so I want to determine the molality first. What's the molality of that solution? What's the molality of that solution? It is the number of moles divided by the kilograms. So what is 0.5 moles divided by 1 kilogram? 0.5.